This is part 3 of lecture 7. In this part we'll be talking about multivariate examples of maximum likelihood estimation that will extend the results we covered last time in single variable estimation. Now before we go into this, I'd like to do a short review of differentiating vector functions. The key difficulty in dealing with multiple parameters that we need to estimate is now that in order to optimize these, we have to differentiate a function of multiple variables to find the optimum. And so, of course, differentiation requires multivariable calculus, which is something that some of us may have forgotten or just need a slight refresher course on. So let's just go through the ideas behind this, and I'll talk mainly about the kinds of vector functions that we'll see in this class, mainly linear functions and quadratic functions. So let's think about what a function of multiple variables is, and in this case what we'll do is we'll look at the simplest case, and so instead of looking at a single variable, for example, y is equal to f of x, what we'll do is look at y is equal to f of x1 and x2. So typically what we'll do is we'll have a function here, x1 and x2 of x1 and x2, right? And this third dimension will be y, and we can think of y as kind of being the height of a surface, and x1 and x2 as locating a point on Earth. For example, it might be the latitude and the longitude, at least locally, if we're considering a local part of the sphere that looks like a plane. And so y then might be the height over the Earth's surface. And so we might have different kinds of surfaces. For example, we might have something like a hill that would start out at a peak value there and then kind of come down like this. So this is kind of a hill, it's kind of coming down, maybe like this, in different directions. Okay. So this is the function y of x1 and x2. At every point you have a height. And so the derivative of dy dx is a vector, right? And that's just obtained by differentiating y in each direction along the x1 and the x2 axis. And what that vector does is the vector gives us for each point, it gives us the direction which we need to go up the surface. So that's the gradient. The gradient tells us how things are changing, and the gradient in a multivariable system tells us the direction of multiple increase. Right. In 1D functions, we actually have the same thing. It's just that there's really only two directions you can go, up or down. Right. So if I have, let's say, a 1D function, maybe a parabola or something like this, then in this case here, the derivative is like this in this case, and it's like this in this case here. So here the derivative is positive, meaning that in order for me to go up, I have to go in this direction. In this case here, the gradient would be in this direction, which means that it would be negative, and I would want to go in this direction to go up. Okay, so let's take a look at several examples of this. In particular, we'll look at two examples: the constant vector times a vector. And so here we have a constant vector c times x, and so here this is c1 x1 plus c2 x2. And so in this case here, if I look at the lines of constant height, right, let's say I say c1 x plus c2 x is equal to, let's say, 0. But then what I can do, so this is x1 and x2, then if this is the x1 and x2 plane, let's call this x2 and this one x1, then I can write this one as x2 is equal to minus c1 divided by c2 times x1. Right? So that's just a slope line with, let's say, slope, let's say C1 and C2 are 1 in this case here. It would just be a slope here with slope minus 1, but anyways, it's just minus C1 divided by C2, right? And then for any other point here, let's say I say this is not 0, but some other value, all that would end up happening here is that I would add an offset to this, right? So for example, if I looked at C1 x1 plus C2 x2 is equal to 1, then I would get x2 is equal to 1 over C2 plus right, minus C1 divided by C2 x1. Right? So that is exactly the same slope, it's just moved up by 1 over C2. Right? And so in that case I would get something maybe that looks like this. And so the level sets of this function are all parallel lines, and what this means is that this is just a ramp, right? And in particular, I'm going to go up in let's say this direction, like this, okay? If C1 and C2 are both positive. And so let's take a look at what the derivative is, right? So if we take the derivative, we just differentiate y with respect to x1, and when we do that, we just get c1, and we just differentiate y with respect to x2, and when we do that, we just get c2. And so what that says then is that I get this direction here, and that vector here, let's draw it over here, would be in the direction c1, c2. And so we can see that basically we can steer the direction of this ramp any way we want just by changing C1 and C2, right? So for example, if C1 was 1 and C2 was 0, then the ramp would be going up in this direction. If C2 was 1 and C1 was 0, then the ramp would be going up in this direction. And depending on how I can choose these, I can have the ramp going up in any other direction that I want. Now, since x1 transpose c is equal to c transpose times x, then in this case, if I differentiate this with respect to x, I also get c. Now, I think it's always instructive when we do these kinds of differentiations to think about, well, what's the analog in 1D, right? So an analog in 1D is just simply y is equal to c times x, right? It's just a line here that goes up with slope c. And so if c is positive, the line goes up. If c is negative, the line goes down. And so that's this, and so this is exactly the analog of that. Things become a little bit more difficult when we talk about a quadratic form. So when we have a quadratic form, we're generally speaking about an equation like this, x transpose times a times x, where again in the simplest case we're thinking about a 2D vector, x1 and x2, and then in that case this A is a matrix, it's a 2 by 2 matrix, and if I go ahead and expand this matrix multiplication out, I can, let's say, do this times this. Right? And so what I'm going to get is a11 x1 plus a12 x2. That's this first line here. And then a21 x1 plus a22 x2. That's the second line there. And then when I multiply this thing out, I get a11 x1 squared, a12 x1 x2, a21 x2 x1, and a22 x2 squared. So I get this expression right here. And so you can see here that this is indeed a quadratic. It just contains terms of order 2. And also you can see here that there's kind of an ambiguity between a12 and a21 because in this case here, this thing here is just a12 plus a21, x1, x2, right? So I can actually have many matrices here that result in the same quadratic form just by adding something to x21 and subtracting something from x12. Right? So in other words, I can move this up by a little bit, move this one up by a little bit, and move this one down by a little bit. And so in that situation, we don't like to have that ambiguity. So generally what we do is we assume that A is a symmetric matrix here, in which case A12 and A21 are exactly the same. Right? And I can always do that because if they're not the same, I can always add a little bit here or subtract a little bit here, however I need to make those two things the same. So any quadratic form that I have can be expressed using this matrix, and I make the matrix unique by making sure that it's symmetric. Now let's look at what happens when I differentiate this thing with respect to x1 and x2. And so when I differentiate this with respect to x1 and x2, the first one I differentiate with respect to x1, I get 2a11 x1, right? And then a12 x2, right? And then a21 x2. And when I differentiate with respect to x2, this thing is 0, and then I get a12 x1, a21 x1, and then I get a 2 times a22 x2. So now it turns out that if I look at this thing, I can write this one as the matrix A times x1 plus the matrix A transpose times x1, x2 as well. Right? I can just do that just by multiplying it out and checking to make sure it's the same. Right? So I get an a11 x1, I get one of these, and the next time I do an a11 x1, I get the other one, and then I get an a12 x2, which gives me this one, and an a21 x2, which gives me this one. Okay, so that's the first line, and you can do the second line yourself. And so I get this form here, but now since I've assumed that A is symmetric, right, what I can get is that the derivative of the quadratic form with respect to x is just 2 times the matrix A times x. And so if I think about the scalar case, I have y is equal to, let's say, ax squared. Then when I differentiate this, I just get 2ax. So this is exactly the analog of that, just using vectors and matrices rather than simple scalars. So a quadratic form generally has some kind of function. For example, the easiest one would be some kind of a parabolic bowl. Right, so let's take a look at that in this example here. So here I'm going to choose A to be the matrix 1, 0, 0, 1, the identity matrix. And in that case, when I put this into here, then I just get x1 squared plus x2 squared. So if I go back, if I look at this, only this term here is 1, and this term here is 1, and these two are 0. So I get this. And now the level sets of this, where this is a constant, are just circles. So if I look at the x1, x2 plane, then the level sets will look like this. Equals some kind of constant k, let's say. And then if I twist this kind of on its side, so that we can kind of get a better 3D view of this, x1, x2, and this would be, let's say, y. So let's call this thing y. Then I would get something that starts out here at the origin. It would go up quadratically in this direction. It would go up quadratically in the x1 direction as well. Right, and then in this region here, all the level sets would be circles. So this is a parabolic bowl, and you can kind of think if I put a ball here, what would happen is the ball would roll down and end up here at the bottom of the bowl. So let's take a look at the derivative here. So the derivative here, you kind of imagine, should be pointing out, right? Should be pointing straight out this direction, so that if I look here, I'm basically going to go up the bowl just by going away from the origin. Right? So the derivative should look like this. Let's take a look at whether or not that's true or not. We differentiate this with respect to x. We get 2ax. A is the identity matrix, so I get 2x, so this is 2x1 and 2x2. So at this point, let's say this point here was 1, 1. Then this vector here would be 2, 2. Right? So it would be pointing exactly in the same direction of this. It would just be twice as long. So I don't draw it to scale here, but I'm just trying to show you the direction. And so here, if the direction here is minus 1, minus 1, comma 1, then this one would also point in the minus 1, 1 direction. Okay, and so everywhere you go, it's going to be pointing out, which is exactly what we expect. So in summary then, we've seen that when we differentiate vector functions, at least for the linear case and the quadratic case, we get things that are very, very similar to that which we expect from the scalar case. And so now with that, we're kind of ready to take a look at the example that we touched on at the end of the last part, which is the multivariate Gaussian. So we have n samples drawn from a multivariate Gaussian with unknown mean but a known covariance matrix. So in this case here, what we're talking about is we have a set of data points in the 2D plane. Let me just draw this out for you. So we can kind of visualize what this is. We have a set of points here in the 2D plane. And we want to say, well, what is the distribution that generated these points? And we're going to assume, okay, it's some kind of Gaussian, and because the covariance matrix is fixed, the Gaussian hill always has the same shape. So if we put a Gaussian here, let's say you can put it anywhere, we can put the Gaussian here. This is obviously not a very good description of those data points, right? Because it's centered over here, but most of the data points are over here, and so probably a better description of the data points would be by taking this Gaussian and not changing the shape at all, because the shape is determined by the covariance matrix, but shifting it over so that it sits kind of on top of all these points that we assumed were generated by that Gaussian. So what we want to do then is take this hill and shift it all around to all the different locations to try to find out where the best location of the mean vector here is. And so I'm going to call the mean vector here mu1 comma mu2, okay, or vector mu. Okay, so let's take a look at that mathematically. So we have n samples drawn from a multivariate Gaussian with unknown mean vector mu but known covariance matrix sigma. That has this form here, and we're going to find the log likelihood, right? And then for all the data points, we simply just add all the log likelihoods together. So I'm just going to look at one single point, and then I'll do the summation later on. So let's just take a look at this one single point, and then take the logs. Now again, what I can do is when I take the logs, I can just convert a multiplication of this times this into a sum. Right? So I get the log of this, and again, 1 over this is the minus log, so I get minus 1/2, because I'm raised everything here to the 1/2 power, so minus 1/2 times log of 2 pi to the nth power times the determinant of the covariance matrix. Minus the log of this, but the log again undoes the exponential, and so I get, sorry, it should be the plus the log of this, but the log undoes the exponential. I get a minus here 1/2, and the same thing, just copy this thing down here. Now I want to find the optimal value of mu, so I just differentiate this thing with respect to mu. This first term here differentiates to 0, and this one here is just the quadratic form, the exact same. This is xax, right? The only difference is I have to subtract the mean. But here, if I have something like xax going back, I just get 2ax. Right? So here x is just x minus the mean, so I have 2, and that cancels the 1/2, so I get 2 times 1/2, or 1, a, which is sigma inverse, times the x, which is xk minus mu. And then I have a minus sign here, but then when I differentiate with respect to mu, I have to use chain rule, and so the minus sign here and the minus sign here cancel, so I don't get any minus sign there. So now, if I want to take into account all the data, what I do is I simply sum this condition over all the data points. So I sum the log likelihood over all the data points is just sum of this, and I set the whole thing equal to 0, but in order for this to be equal to 0, what I can do is I can pre-multiply this thing by sigma, because the sigma here is all the same for all the data points. And so I can pre-multiply by sigma, and then I get this whole thing here is equal to 0. And then again, what I can do is, when I sum this one out, I get a sigma k is equal to 1 to n of xk minus n mu. Right? So I just apply the sum here and sum here separately is equal to 0. And when I solve that, I just get this. So that's exactly the same answer we got before. Now let's take a look at the final example here. And the final example here, we're going to kind of slightly relax the condition on the Gaussian, and now what we're going to do is we're going to allow the mean to be unknown and the variance to be unknown. And so in this case here, what we have is we have, let's say, a set of points that we assume is described by a Gaussian, and now, in addition to being able to adjust the mean, we can also adjust the variance. So the question is, which of these Gaussians would be the best? Obviously, this one here is probably too narrow. This one here maybe is a little bit too wide, and so it's probably somewhere, the optimal variance is somewhere in between these two values. And so we'd like to find that value. So we're going to set our unknown parameters to be mu and sigma squared. And then I'm going to write the likelihood, and then take the log likelihood. And so I get minus, because I have 1 over, 1/2, because I have the square root, the log of whatever's inside here. So log 2 pi sigma 2, where sigma 2 is just, theta 2, where theta 2 is just sigma squared. Minus this, because again, I get plus log of x, but the log and x cancel each other out. So I just copy this thing down here. And now I differentiate this with respect to sigma 1 and sigma 2. When I differentiate with respect to sigma 1, this thing disappears. Right? And so the only thing I'm left with is 2 divided by 2, so 1, and I get a minus xk minus sigma 1, but then when I differentiate with respect to sigma 1, I have the chain rule, so the minus minus cancels. So I get xk minus sigma 1 divided by sigma 2. When I differentiate this with respect to theta 2, then remember, because dx of log of x is 1 over x, when I differentiate this with respect to sigma 2, I just get a 1 over sigma 2, right? So I get a minus 1/2 times 1 over sigma 2, or sorry, theta 2, plus the derivative of this with respect to theta 2. So here I just copy this one over, and now I have something, a constant here. This whole thing you can kind of think of as a constant, and I have 1 over theta 2. So if I differentiate of theta to the minus 1, or 1 over theta, right, that's minus 1 over theta squared. Right, so let's say this is theta 2. And so I just get this whole constant here times 1 over theta 2 squared. Now if I take into account all of the data, then the only thing that happens is I just get a sum here. So I sum over k for both of these. So when I sum over k for both of these, I get this equation here, and I set the whole thing equal to 0, so I get the sum of those things equal to 0. And then when I sum this thing over k, there's no variation here with respect to k, so I just have n of these, where n is the number of data points, right, plus the summation of k over all of these guys here. And I set the two of these things equal to 0. So let's take the first equation there, which is this one here, right? And now it doesn't really matter what theta 2 is as long as it's positive, right? So I can ignore this one or just multiply through, and I just get the same thing I got, sum of this, and I get n of these, and so this is just the maximum likelihood estimate of the mean is just the sample mean. This is exactly the same thing we got last time. And now for the second equation, which is the new thing, which is looking for the variance, I can multiply this whole thing by sigma 2 squared. So if I multiply this whole thing by theta 2 squared, then I get a theta 2, and I get a theta 2 squared here, right? Let's say put the theta 2 squared over here. And so now I get a cancellation here and a cancellation here, right? I cancel out the 2 here, and I cancel out one of these guys here. So I just get a theta 2 times n, plus this, and there's no theta 2 inside here, right? So I can move this guy over to the other side, and I get this, and then I just divide by n to get this. And so what this says is remember theta 2, theta 2 is sigma squared, the variance. And so what this is just looking at the average squared distance between the data point and the sample mean. So intuitively, this is kind of consistent with our idea of the variance as being the average squared distance from the mean. The only thing I've done is replace the average by the kind of sample average of the mean, and the average of the squared distance by the sample average. And so intuitively, these results are very appealing. Now I can do the same thing for the multivariate case, and it shouldn't surprise you that I'll get almost exactly the same kind of equations. The only difference here being that instead of doing this squaring thing here, I'm going to take x minus the mean times x minus the mean transpose. This is just to take into account the fact that I have a vector. And this is going to actually give me a covariance matrix, right? Because this vector is a long vector, long skinny vector, and this one is a long flat vector. And so when I multiply this times this, I'm going to get kind of a square matrix like this. And so if this is n by 1 and this is 1 by n, then this is going to be n by n when I do the multiplication. Okay, so that's it. In the next lecture, we'll start talking about estimator bias.